In this lecture, we are going to discuss one of the transport property of solutions is known as diffusion. So here diffusion is a macroscopic motion of components of a system that arises from concentration differences. For example, if we have two chambers of a solution in which phase 1 have concentration of J species is 1 and the other one have concentration of J species is 2, and if the concentration of species J species in phase 1 is less than the concentration of this species in the phase 2, and if we remove this partition, then this species will tend to move towards the phase 1, and the net flow of this species is from the phase 2 and phase 1, and these flows continue until the concentration and the chemical potentials of the species is constant throughout the cell. Diffusion is different from the macroscopic bulk flow that arises from the pressure differences, but here this flow is based on the concentration difference. For the bulk flow, for example, if we have two valves where the pressure is P1 and P2, the flow of solution is in X direction, whereas for this valve the flow of solution or the liquid is, or the fluid is, towards Y direction. So here all the particles have same direction of the movement with similar component of velocity that can be either X direction or Y direction, so it should be a unidirectional for laminar flow. But for the case of diffusion, the movement of the particles is random. So for the case of diffusion, the velocity is known as random velocity. So let's understand the phenomena of diffusion from the graphical description. For example, if we have two chamber of the cell having components that are separated into phase 1 and phase 2, and if we remove this the partition, then what happened? The species that are separated from the partition, and when this partition was removed, the phase 2 having concentration is much higher as compared to the concentration in phase 2, which have the distance from this partition is constant. So when this partition is removed, the molecules or the species present, that is the J species, they will start to move towards the phase 1. So in this way the concentration of the species J in phase 1 is increasing, whereas concentration of the phase 2 is decreasing. So we have this type of concentration distribution with respect to the chamber distance from the barrier which was removed. So this is the intermediate time, and enough time is provided to the this chamber in such a way that the phase 1 and phase 2 got enough time that all the species from the phase 2 have been moved to phase 1, and species from phase 1 are also moving towards phase 2 in such a way that overall distribution of the concentration of species J is normalized in every region of this chamber, and the concentration of this species J is equal in all regions of this chamber. So from this experiment we can say that the experiment shows that the following equations are obtained. So what are the equations? So here we have equation number 1, which is known as Fick's first law of diffusion, whereas the number of moles of the J species which are changing with respect to time, this ratio is known as net rate of flow of species J. The unit of this rate is in moles per unit time. This net rate of flow of species J is actually across a plane P. So here we had a partition that have been removed. So here this partition was actually a planar area P, which is at right angle to the x direction. So the area of this partition is given here, where the rate of change of the molar concentration of species J with respect to the x coordinate, that is at the area of plane P in the direction of phase 1, that is parallel to the x-axis, whereas this d is known as the diffusion coefficient, and k is representing the presence of other species which have been moved through this barrier when it was removed, having concentration variation in phase 1 and phase 2. So here we can write this fixed force law for the species K2. So here we have written the value of the diffusion coefficient in terms of all the species present that have been moved due to the concentration gradient. So the diffusion coefficient is expressed for all the species present in the different phases that have been in contact with each other and the process of diffusion is observed. And from this fixed law we can see that the rate of change of diffusion is proportional to the area and as well as the concentration gradients. Greater the difference between the concentration gradient of two phases of a sample, faster will be the rate of change of the concentration with respect to distance, and thus the overall flow with respect to time. So in this experiment what we have concluded that the diffusion rate is proportional to the concentration gradient and area. So here one more thing is to remember that at start the concentration gradient is higher than the rate of flow of species J from phase 1, phase 2 to phase 1 is higher. So initially the rate is faster, but at the time when the concentration gradient is narrowed, and thus the rate of flow is reduced and eventually becomes zero when the concentration gradient is normalized, and at this stage the diffusion process is stopped. So let's see other variables which also affect the process or the phenomena of diffusion, in which the two important variables are known as temperature and pressure. So here the temperature and pressure are the function of the local state of the system. So the diffusion coefficient is also a function of the local state of a system, thus it depends on the temperature and pressure, and this diffusion coefficient is actually the function of temperature and pressure of the system, and the important variable was concentration of the species I, that can be either J or K. So here we have seen that in diffusion experiment, what we have measured the concentration with respect to distance. So here concentration is the function of distance at time t. For particular dimension of x or value of x, we can have different values of the concentrations at different times. And here, if the two solutions differ substantially in initial concentrations, then since the diffusion coefficients are the function of temperature and pressure and concentration, so here concentration is the one of the important factor that decides the value of diffusion coefficient that varies substantially with distance x. So if this distance is considered, the diffusion rate is faster as compared to the distance that is closer to the space from where the partition has been removed. Now let's discuss the change in volume. And so here, if solution 1 in phase 2 and solution 2 in phase 2 are mixed with no change in the volume, then we can show that the diffusion coefficient for that is expressed in equation 1 and the diffusion coefficient that is expressed in this equation number 2 are equal. So I have represented this diffusion coefficient with dash. So for no change in volume, the two diffusion coefficients are equal. So this diffusion coefficient can be expressed as the subscript k and j, as we are discussing about the species k. And for gases, this condition is fulfilled usually. But for the case of liquid solutions, these two diffusion coefficients aren't equal but have a difference in, that is the negligible change in volume. So we can say that both the diffusion coefficients are equal or considered equal for the case of liquid solutions. And this condition is true for the slight difference in concentration of the two solutions that are occupying the two chambers of the experiment. So here this condition must be satisfied in order to make the two diffusion coefficients nearly equivalent. But for the case of larger difference in the composition of the liquid solutions that are separated with the removable partition, and the rate of diffusion is actually depend on the diffusion coefficient, which also varies with the temperature and pressure variation, as well as the difference in the composition of the two phases that are separated and then allowed to mix through the process of diffusion. So for the case of liquid solutions, the diffusion coefficient varies strongly with composition, whereas the constant increases with increase in temperature. Let's discuss the example of the water ethanol solution. And we can see from this graph here the concentration or the mole fraction of ethanol is given here with respect to the diffusion coefficient. So here we can see that the plot of mutual diffusion coefficient versus composition for water ethanol solution at 25 degrees centigrade and 1 atmosphere is showing that the minima nearly at 0.3 mole fraction of ethanol and the values of the diffusion coefficients at the 0 or 1 mole fraction of ethanol are being extrapolated from the plot. So from this plot we can see that the value of the diffusion coefficient does depend on the ratio of the mole fractions of two solutions, that is for water and ethanol. So these values at extremes are known as diffusion coefficient at infinite dilution. So here we can find which one is the diffusion coefficient for infinite dilution when the solute or the solvent. So let's see from this description. For example, if we have DIP infinite, that is the diffusion coefficient for IB for infinitely dilute solution of when solute is I in solvent B. And for this case, the infinitely diluted water in the ethanol solvent, the diffusion coefficient at infinite dilution is given from this point. So the diffusion coefficient of water when it is acting as solute in the solvent is at infinite dilution is equal to 2.4 into 10 to the power minus 5 centimeters square per second. That is this point, which is obtained from the extrapolation of these intermediate plots. So for the case of gases, we can have a constant value of diffusion coefficient for any composition of two gases, whereas for liquids we have either minima or maxima depending on the type of intermolecular forces that have been developed during the mixing of these two solutions, or they can be linear when there is a difference in the diffusion coefficients of the two extremes or at infinite dilutions. Until now we have discussed that the rate of diffusion that is controlled by the diffusion coefficient is depending on the difference in the composition of the two component of the chamber that have been separated from the partition. Here we have two component of the chamber that are separated by a partition having a surface area A. So the concentration gradient of the composition of these two solutions and the area of this partition is directly related to the rate of diffusion and thus the diffusion coefficient. But how far a distance from the partition these particles can diffuse from one phase to the other phase. For example, if we spray any perfume or any gas in one chamber of our room, so how far it can reach to the other corner and how much it will take time. And if we consider the kinetic theory of gases, that the speed of gases is relatively high, but if we feel that the movement of the sprayed molecules to the other corner of the room is time consuming, it means that the mixing of gases, the process is slow. That means that the rate of mixing is not equal to their speed of motion. Rather it is slower relative to the speed of gas molecules. That is due to the collision between the different molecules of the gas that cause the change in the direction of motion, and thus zigzag path is observed instead of the linear path. Due to this random movement of the gas molecule, the speed of the mixing or the rate of mixing of the gases is slow as compared to their original speed of movement. So how we can describe the phenomena that how far on the average molecule can move to a distance in given time interval. So it is defined by the Einstein equation, which gave that the average of the square of displacement is equal to 2dt, where d is the diffusion coefficient and t is the time interval. Why we are taking average? Because the displacement is not linear, but it's following a zigzag path. So it's better to use the root mean square distance that is covered by the molecule. So it is equal to the square root of 2dt. So what's the real cause of the diffusion process? It's actually result from the random thermal motion of molecules. So practically this random motion can be studied or observed indirectly by its effect on the colloidal particles suspended in a fluid. So these particles undergo a Brownian movements. So why these kind of Brownian motion is observed? That is due to the microscopic fluctuation in pressure in the different part of the fluid. So this Brownian motion is actually the really fundamental cause of diffusion process. So the random motion of the molecules is due to the experience of force that is based on the time, that is equal to the mass of the molecule. Let's call it in x direction. So we have to define the acceleration, and acceleration is actually the change in distance with respect to time, and by multiplying with the value of x distance, we get equation number 5, and this total force that is acting on the motion of the molecules, that is the random or Brownian motion. So here the factor known as the frictional force that must be subtracted to the overall force that is experienced by the molecule is given as so here this small f is known as frictional force. That is experienced due to the collision, or for the case of liquids, that is due to the relative motion of the different layers of liquids, that is based on the viscosity. So this force can be arranged for many particles, and Einstein averaged this value for many colloidal particles, and assuming that the colloidal particles have an average kinetic energy equal to the average translational energy, that is actually expressed as 3 by 2 kT for the molecules of surrounding fluid. So the average kinetic energy of the colloidal particles is actually equal to the translational energy of the molecules which are surrounding this fluid. So the average square displacement in x direction is given as average distance square. So these symbols are showing the average, and it's a difference. Displacement square is equal to 2 kT over F into time t. So this is equation number 7 that is given by Einstein, where F is the frictional force, K is the Boltzmann constant, T is temperature, and small t is time. And if the particles are spherical, then the particles having radius r. So for these kind of particles, the frictional force coefficient, that is F, is given by equation 6 by eta r. So this equation is known as Stokes law, and by comparing equation number 7 and 8, we can write the average square displacement in x direction is actually equal to kT over 3 by eta r into t, which is applicable for the spherical particles. We get question number 9. And from our previous equation that is given by Einstein for the average square displacement in x direction, that is depending on the diffusion coefficient and the time that is required for the average moment. So here by comparing equation number 3 and 9, we get equation that is the diffusion coefficient describing the Stokes-Einstein law, where this R is known as hydrodynamic radius, which also including the solvent molecules, or if the solvent molecules are water molecules, then we call it hydrodynamic radius or radius of solvated molecule. So this diffusion coefficient can be calculated from the electroanalytical techniques or the dynamic laser light scattering technique. This equation used for the calculation of the diffusion coefficient using dynamic laser light scattering technique, and this equation is used for the calculation of the diffusion coefficient using electrochemical method. Here mu is the mobility, R is general gas constant, F is the Faraday's constant, whereas C is the concentration, N is the number of moles, and this is the scan rate. So for unknown compound, we can calculate the hydrodynamic or radii or the radii of the solvated molecule if they are spherical, using this Stokes-Einstein law that is explaining the diffusion of spherical particles. Or conversely, if you know the hydrodynamic radii, you can calculate the diffusion, and from here you can also calculate the mobility of the solute particles.